Okay, now we continue the concept of the Hipparchus scale and apparent luminosity, and we start with apparent visual magnitude -2.5 log apparent luminosity over apparent luminosity of sun, and we use the definition of apparent luminosity is that absolute luminosity over 4 pi d squared. I have a previous video where I talk about this. The 4 pi d squared comes from the surface area over which the light spreads out from a star, and then we're going to also incorporate the conversion between the light year and the astronomical unit system, 63,239.6717. So I'm going to take this equation, put it in here, -2.5 log, this is going to be absolute luminosity over 4 pi distance squared over absolute luminosity of sun over 4 pi distance of sun squared. So then the 4 pi is going to cancel, and then we're going to have -2.5 log of, this is absolute luminosity of a star divided by the distance of the star squared, and then absolute luminosity of the sun is in the denominator. Okay, and then the distance of the sun goes to the numerator, distance of sun squared. Okay, so now I'm going to say distance of a star, let's say the star is 10 light years away, 15 light years away, 16 light years away, 100 light years away. So I want to say the distance is in light years, but then this distance of the sun is 1 AU. So what I'm going to do is say the distance of a star, let's say it's 10 light years. The conversion is 1 light year is these many AUs, right? 63,000 something something. Then I have to square that. So if I want to write this distance in light years and be able to cancel with this distance, the distance of the sun is 1 AU, I need to put this conversion in here. Okay, so I will have, I'm basically building an equation so that if you basically tell me the distance of a star in the light years, I can then convert it and calculate what the apparent luminosity of that star is. So I have here mv is equal to -2.5 log. I'll put here absolute luminosity. Okay, and then I'll put here 63,239.6717 squared. Okay, since that one is the conversion, but I have to square it, right? Then I'm going to have the star squared. Okay, now you can tell me a particular star is 30 light years away. I can put here just 30 squared, and then multiply it by this thing squared. Okay, and then over here, what's going to happen? The distance of the sun is 1 AU. So 1 AU squared. That AU and this AU will cancel, right? AU, you squaring both of them, you cancel. So we just need 1 squared here. And then over here, absolute luminosity of the sun. Absolute luminosity. We close the brackets. Okay, so let's see how this equation will work. Okay, now I need to also put the 26.74 because that's my reference. That's the apparent luminosity of the sun on the Hipparchus scale, right? So now let's practice this. Let's say there's a star, the absolute luminosity of the star over the absolute luminosity of the sun is 10,000. Let's say the distance of the star is 30 light years away. So we're going to have mv is equal to -2.5 log. This divided by this, the ratio of the two is 10,000. So 10,000, this is just simply 1 over this number 63,239.6717 squared times the distance 30 squared. Okay, so let's go, and then we're going to put the -26.74. So it's going to be all this came out to be 21.39, and then minus 26.74 Okay? So when you subtract that, so you get negative 5.349. So if there was such a star that was 30 light years away, and it was really bright, 10,000 times brighter than the sun, okay, that star would look brighter than the star Sirius A. Remember in the previous video I said Sirius A was a negative 1.4. This star would appear brighter. So there is no such star. There is no such star that is 10,000 times brighter and only 30 light years away. So you could practice this on pretty much any kind of example. You can make a star closer, farther, much brighter, much dimmer. Let's just do one more example. Let's say there was a star a lot brighter, okay? So let's say this one was 150,000 times brighter than the sun. And then let's say the distance was farther away. Let's say 1,200 light years away. Okay, so what would that be? So 1,200 light years away, that would make it pretty much in our galaxy. Okay, so the Milky Way looks like this. We're over here. The thickness of the galaxy is about 2,000 light years. So this star would be somewhere here, somewhere in our galaxy, 1,200 light years away, 150,000 times brighter than the sun. So that's actually pretty bright, right? So we put here 150,000, okay? And then all we change, we keep this the same, and then we just put here 1,200. 1,200, and we square that. So we can just go back into the equation that we just had. 1,200 squared, and divide by ln. Now this one came out to be, this whole part came out to be 26.46 minus 26.74, and then that gives you what? Around negative 0.3 or something. Is there such stars? Oh yeah, those are the brightest looking stars in the sky. The ones that you don't even need a telescope to see. They range anywhere between negative 1.4 all the way to Polaris is about a 2. Okay, so these ones you could comfortably see them in a typical night sky. So if there was such a star like this is a typical star that would appear bright enough in the sky that we wouldn't need a telescope to see. 150,000 times brighter than the sun, 1,200 light years away. So you can practice any combination. Of course, if there's another star much farther away over here, there's another star that is 150,000 times brighter than the sun, but this time it's way on the opposite side of our galaxy. So that would make it maybe from here to here is about 30,000 light years. From here to here, let's say 20,000. Let's say it's 50,000 light years away, right? And we put here 50,000. 50,000. You could practice all kinds of things. If you put 50,000 here, but you keep everything else the same, what changes? So we go back to the equation. Now what are we going to get? Now this whole part comes out to be 34.56. Then you subtract from it 26.74. And that gives you 34 minus 26, roughly around 8. Right? So that star, you are going to need a telescope to see it. Remember, we said anything greater than a 6, you need a good astronomical binocular or a telescope to view that star. So a lot of the stars that are here, even though they're 150,000 times brighter than the sun, you will not see them in the typical night sky. Of course, the other problem is that you're trying to see through the middle of the galaxy, and the brightness of the galaxy here fades everything away. So this equation, you can now practice, you can do different combinations, and it will allow you to calculate the apparent visual magnitude of the star. Now I'm going to make another video that is related to this, and I'm going to change this equation around, and you're going to see the other usefulness of this. Thank you very much.